Hi, good evening, all. We'll wait for 2-3 minutes and then we'll start. Huh? Hi, does my screen visible? Is it visible now?
Yes,
Fine. Yeah. We are already 3 minutes late that we are waiting then. Yeah, this week 8 is exclusively talks about that more problems that we can solve using the divide and conquer technique. So that's what here various 3 or 4 different types of problems are there. So using the same method of divide and conquer which you learned earlier, that can be applied on other kind of applications. So let me see that. So what really we can do more with divide and conquer. So this is a list of sequential slides. Yeah. So this could be that complete slide till that 1 to 5 is available in 6. So you already know that divide and conquer is a simple technique. It is splitting the problems into subproblem, splitting the problem into subproblems. So like, one problem is maybe divided into many teeny units or teeny parts or short compartments. Each of them is being solved independently. So once that solved one is there, again it is joined. The solutions are joined. So once it is solved, the solutions are joined. So joined solutions. So
Like
finally,
your connection is a problem, I think. I don't
hello.
know whether it is only for me or
Yeah.
somebody else also.
Hello. Yeah.
Your connection appears to have some problem.
What is the problem? Are you able to hear me? Hello.
Is it good for everybody? Yeah.
we can hear you, sir.
Please, others, please.
I can hear you clearly.
Okay. Okay. Fine. Can you look at your side, please? Once you look at your side, yeah, you can rejoin or something. Somebody is facing problems. Okay. Yeah, it is splitting the problems into the smaller problems. Whatever the sub problems are solved, the solutions are joined. So we already did the two kinds of problems which you are using same kind of technique. So the MudSat and QuickSat. So both of them are using that dividing a problem into sub problems, but here the difference is simple. So if you think about the MudSat, so complete list is whatever that list of elements are there, they are every time divided into the two parts. Like, you know, if it is 8 elements of part, so you have that first split, something like this. And then we have the second split is there. You might have the 2 elements and 2 elements split. So here one thing should understand that here also divide and conquer policy and QuickSat also divide and conquer policy. But the MudSat requires that space is more, because every time in the recursion, it creates a sublist. So the space complexity is somewhat increased. It means that space complexity is 4. External memory space is created for every sublist. So in the case of QuickSat, it's very simple. It is also divide and conquer. But what happened, you know, internal partitioning is done. Like you are taking one of them as a pivot. Let me take, this is the pivot. So every time pivot is going to scan it from left, and similarly it will scan it from right to pick out the suitable position. So once it is there, there is a swapping is done. The pivot is swapped to its suitable position. So that is happening, so that there is no additional space complexities involved in the QuickSat, but it is also having same kind of divide and conquer policy, which you already learned 2 applications. Both of them are MudSat and QuickSat is using divide and conquer, but only the difference is here the external space is used in the MudSat, but QuickSat is not using external space. Inside of it, only the splitting is done only by simple swapping of the pivot element. The pivot element is swapped with suitable its right position. Once it is right position is placed, then it will select another pivot element. So let us, so some more examples they want to discuss. So like in this particular week number 8, what we can solve still using the same kind of technique. So if you are going for the single sequence of the slides, recommender system. Yeah, up to here is a single sequence of slides. The recommender system. So let's they have been solving the recommender system. Recommender system usually works that if it wants to recommend a particular product, definitely it will verify that your likes and dislikes, comparing with your friend first. If the friend and your likes are matched, so whatever that purchased, frequently purchased item by your friend, similar kind of items, first it is going to give a recommend for you, like it gives you the alert, like this particular item is good. So that kind of alerts you get it. So that's what basically happening. Of course, it is based on the past history of your purchases also it is happening. So in this particular example, they have taken that recommender system of movies. Like if you look at that recommender system, so in this particular example, so they are comparing the rankings given by you and your friend. For example, so there is a list of movies was taken. Let's you take a sequence of movies. So these movies are 1 to 5. So the ratings are 1 to 5. What exactly mean that? So 1, 2, 3, 4, 5. So 1 is the best ranking. The lower number indicates the best ranking. Higher number indicates the poor ranking. So here you have been given the first rank for better rank for the D, B, C, A, and E. This is you. You have given it. But your friend has been given a different kind of sequence. He has chosen that B is the best movie, A, and then C, then D, then E. The same thing it has been given like here. So here 1, 2, 3, 4, 5 is that movie names. So we are giving, movie ratings, which is the best rank and worst rank. In that, we are placing your wish, which you want to give it the best. D, you want to give the best. B, you want to give it the second best, something like that. So if you compare that your your ratings and rankings and your friends' rankings, so D is there. So you have given D over B. So like, D has been decided as a best movie comparatively B. But in the case of your friend, he has decided B is the best movie comparatively the D. That's what they are discussing. So what exactly, one thing you can see that you and your friend both marked, one similarity is there, both marked B is better than C. Like you are given best ranking of B over C. And similarly, your friend also given that B is the best movie over C. That's not issue because internally we are comparing. So what ranking you have given? B is given best movie. Of course, you have given that second rank for the B. Your friend has been given that first rank. It's not an issue. But only thing is, are you crossing that both of them decided that B is better than C? Yes, both of them decided it. But once you think about that one more thing, you rank D is better than D. But your friend has ranked that B is better than D. So in that case, there is a difference is there. There is a comparison of rankings. Your friend and your rankings are somewhat different. So this different kind of opinions we call is that inversions is there. Like, so that's what they are called. It is comparing that based on the inversions. So what really your opposite friend is choosing in opposite way. Like what do you feel you are good, that he said it is not good. So what you said it is poor, and your friend says that it is good. So something like opposite kind of opinion. So that kind of inversions is there. We are finding that inversions using the divide and conquer policy. So let me see that inversion, what exactly inversion means that. So here, if you see that the continuous inversions, they want to talk about. Yeah, this is all continuous 2-column slide. So yeah, here it is stopped. Yes. So really, what is inversion? Inversion is simple. So it is a pair of movies ranked in opposite direction. Like you rank is D above B, and your friend is ranked that B is above D. So for example, both of them are given that similar kind of rankings. Then what do you say that your friend, like comparison between you and your friend? So both inversions are 0, no inversions. Then both of them, your friend and you, are identical. Both of them are identical. Both of them are same. For example, if your opinions are opposite in the direction of your friend, so then we can say that they are saying it is not similar. You and your friend are not similar. If that particular inversions are increasing, so listen, that inversions maximum, it goes to that n into n minus 1 by 2. For example, in the previous slide, you have seen that there are the 5 movies. 5 movies are there. Of course, it is 5 rankings we are giving for that ABCD. Each of them is 1 to 5. So the maximum inversions possible is 10. Like n into n minus 1 by 2 is maximum. Maximum is inversions are 10 only. So like each pair is like, where it is different. So that is called inversions. What exactly the inversions is that if both of them are having no inversions, like no pair of things are different, like you have seen a difference between the D and B. So such differences are not there means both of them are same. Your friend and your opinions are same. If that inversions are like 2 or 3 and 4 and 5, it's keep on increasing. That stands for the
excuse me.
Yeah.
How this formula is arrived, sir? N into n minus 1 by 2.
No, it is very simple. No, it is, you are comparing each element like A and B and C and D and E is there. You compare A with B and A with C, A with D and A with E. Similar way, you are comparing B with C and B with D and B with. Like, you are comparing that each particular pair of elements.
Okay.
You are comparing this one with remaining 4.
Okay.
So this one with remaining 3. I hope you understand.
Okay.
So that each pair of them is called one inversion if any difference is there. So in that way it is arrived. Maximum you get that 10 inversions only. Fine.
Okay.
So here they said it is see permutation. Fix that order of one ranking as sorted. Like one of the order is ranking is sorted like 1 to n. Let us we consider that our ranking is constant. So whatever we said the table, no. So earlier table. So we don't see that our thing is fixed. One of them we fix it is so our rankings are fixed. Like oh sorry, yeah. Here in this our rankings we made it constant D, B, C, A, E. We don't want to check it that inversions in this because right now I want to check the recommender system for our particular account. So I don't want to change it. D1, B is 2 and C is 3 and 4 is for A and 5 is for E. Okay, that is constant. And we choose the inversions in your friend. Like see that permutations. Here it is C. So fix that order of one ranking as a sorted, like whatever it is there, that is as it is. Other rankings is a permutation, like your friend rankings you are taking. Other means here it is, you know, your friend. Your friends, we are taking that permutations, we are trying to find out it. So here inversion means where it is a pair I and J, I less than J, where the J is before appeared before I. So let us, if you see that next particular slide, you can see what exactly here is. Each pair they are saying. For example, 1 and 3 is there. What does it mean that 1 and 3 means that 3 is appeared before 1. For example, 2 and 4 is there. So it is inversion of 2 and 4 means 4 is appeared than 2. So I'll show you that where it is that happening that. So really I should be less than the J. So it means that J is appeared before that I. That is what it senses. So we see that next explanation where they have been comparing it. So this is a sequence. What really inversion means they want to tell you. We don't want to check the inversions in the current ranking. Like one of them we fix it as a sorted order. And the second one, other ranking means your friend rankings, we are checking the permutations and combinations. So not the combination, only the permutation. So let me see that there is a counting of inversions is there. The sequence, yeah. Yes, here it is. See, look at. Already I said it. The inversions are always n into n minus 1 is the maximum by 2. It is a maximum 10. In the case of our example, we have taken is 1 to 5. See here, this is yours. Your particular thing is constant. Like your particular thing is already fixed. D and you have given B as per that list. C and then A and then E. This way you have given it. So we don't want to do any kind of thing in this one. So D, B, C, A, E, that is your particular thing is as it is. We don't want to do any kind of changes. But in the case of your friend's ranking is there. So your friend is given that B, A, C, D, E. If you think about B, A, C, D, E, the ranking of the B is 2. Am I right or wrong? This one, no?
Yes, yes.
It is inverted. And A is 4. Because as per that, we have been one of them should be constant, ordered and sorted. And the second one, we are trying to find out the permutations. So 3 is for C, D is for 1, and E is with rank of 5. So now we want to find out the inversions in your friend, not you. Because the recommender system is working on in your account. So your friend is considered whether a movie has to be recommended for as whatever your friend has been liked. So that similarity you want to check it in your account, not in your friend. If your friend is working, then your friend is going to be sorted already and it checks that inversions in your account. I hope you understand. Fine.
Sir, can we make it 10 here? How do we really handle 10?
10 also, see, so we are taking that alphabets
Give
that
a
from the
combination
E.
to get 10. give a combination
Yes.
to get 10.
Like 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry. So we go for the next part so that here you can
So
find it.
in fact, you should have the 10 crossings, is it?
10 crossings, how you can get it? See, max, wherever
So what is-
inversion is there, there only inversion. Every crossing is not considered.
No,
So
every
wherever
crossing is an
inversion,
inversion.
yeah,
Every
every crossing, you see, 1 and 1 you are matching, 2 and 2 we are matching. Wherever intersection is happening, here it is intersection.
Yeah. No,
So
that's what I'm
intersections,
asking. You said
ah,
maximum we can get 10, but
ah.
I'm finding it difficult to visualize the
Okay,
10.
okay. What I want to tell you is 5 movies only, 10 inversions you want it.
Yeah.
Am I right? So
Pick
that
any
is simple.
combination and show me 10.
Unique. See, whatever the same thing you can take it, but your friend is complete opposite. For example, you have given that 1, 2, 3, 4, and 5. So your sorting is not changed like D, B, C, A, E. C. So here, whatever E has been given extremely last, no? So your friend is being ranked, E is the first. So that is what he has been given. Like E is going to be first. So your friend is given that E, A, same opposite of it.
Yeah.
So I'm not sure. I'm not sure that whether is really it is 10 is it, but definitely more than 5. So EAC and B. So let me think about B and then D. Okay. So here, if you think about E, so it is 5 here. Am I right or wrong?
Yeah.
Because this is coming here, no?
Yeah.
A, it's coming with 4. Here it is 3. Here it is 2. Here it is D is 1. Is it right?
Right.
So now we try to do that. This is the first inversion, we got it. Fine.
Yeah.
Okay. So then we are doing this one. We got that another inversions. So we got the inversions, we got it, no? So we got 2 inversions here. Yeah, we got 2 inversions here.
Okay.
So then after it, we got here now 1, 2, 3. So till now 3, another 6 we got it. Is it right? 3 intersections we got it over here. So already available 3 is there, 6 it is coming. So the final one we are crossing now. It is crossing almost 4. So we got 4. I hope all that got it. Yeah, it's 4. So 6 and 4. So that's it. Completely opposite. Fine.
Okay. All right.
So your order is not changed. So your friend order is compared with your order. So whatever he has given it. See, look at here. 1 and 2 is inversion in your friend. So what exactly mean that, so 1 and 2, there is a crossing, we got it. There is a crossing between 1 and 2. It means that 2 is appeared before 1. See, look at 2 is appeared before 1. Fine. This is 1 and 2. Similar way, 1 and 3 is there. You can find 1 and 3. See here, 1 and 3 is this one. You got it? 1 and 3. So 3 is appeared before 1. See, look at 3 is appeared before 1. Matching.
Yeah.
So similar way, 1 and 4 is there. You can find it, 1 and 4. So here is a 1 and 4. Exactly here. This place. So at this place also same. 4 is appeared before 1. So all these 2 and 1, 1 and 2. So 1 and 3, 1 and 4. So here what happened, this 2, 4, 3 are appeared before 1. And the last one, 3 and 4. So what is the 3 and 4? See, look at 3 and 4. Yes. So here it is. 3 and 4. 4 is appeared at this place. 4 is appeared before 3, this place. So we check the inversions, permutations in your friend only as per order of you. Your order is not changed. your friend order is changed and inversions are checked. I hope you understand. Fine.
Yes, sir.
Fine. So this is about that, sorry. So in this case, what happened, each and every IJ we are checking. So I said, every pair we are checking that and we are trying to find out the inversion. So definitely it is a more olden approach and traditional approach. So it requires n square. So it is called naive approach. The prof has been said it is. So definitely it requires that n square. So that is exactly what is happening. So somebody raised the hand. Yeah, somebody raised it. Oh, sorry. Okay. So this is about the. Hello.
Sir, I have a doubt. Like,
Tell me.
we are comparing each and every, like, for one, we are comparing for like every other 4 element. So, it is n to n minus 1 by 2. So why not it is n to n plus 1 by 2? Because
See,
we are.
every time, see, look at first time, what happened, first element is compared with remaining 4. Is it right?
Yeah.
Second element is compared with remaining 3 only, no? Because already it is compared with first element.
So it is like 4, 3, 2, 1, 0.
That's
Sum
right,
of
that's right.
sum of n natural numbers n into n plus 1 by 2.
No. It is n into n minus 1. See, look at maximum 10 only, we get a 10 inversions, not more than that. Definitely it is n into n minus 1.
Hi, sorry to interrupt. Actually, it is the
yeah.
sum of n minus 1 natural numbers, which will make
Sum
it
of
n.
n.
Yeah, it's from 1 to 4,
natural,
right? So it will be n into n minus 1 by 2. Yeah.
That's 1 to 4 only.
Yes.
N into n minus 1 means every n. See that. So if 5 is there, 5 into 4, it is 20. 20 by 10. 20 by 2 is 10, no? Anything different?
Got it.
Why
So
it is n plus 1?
Because like
Why it is
if
n?
it is 5, then it is n into n plus 1, but it is 4, then that's why it is n into n minus 1 by 2. I got it.
Okay. Yeah. So now it is counting. We understood. Yeah. Then we see that how it is divide and conquer works. Yeah, it is combination they are going. So how this divide and conquer is applied on your friends' rankings. So this sequence is all of them are same. Where we stop it, please. Yeah, at this place. Yeah, this is here. It is divide and conquer is applied. See, look at here. Your friends list is there. Your friends permutation is already given. So I1 to IN. So first, what do you do is divide into 2 halves. It is first element to half elements. This is first half. We can say first split and second split, which is that second half. Second split. So which you do that similar way that for the MedSat, which you do that. So recursively we count the inversions. So we do that inversions counting in the left partition and the right partition. And at the same time, what do you do that? Add the inversions across the boundaries also. So across the boundaries means that, so between L and R, so what, the intersection is happening. See, look at that. I is in L, J is in R. So where you find that I greater than J, so how many elements in L are bigger than the RS? How many elements you find that? That means where the L is that left part of it, the left part is occurring. So before that R, so that one we are counting. So how to count that inversions of that we are doing that merge sort option. Same merge sort, what do you do that? Split and then solve it, then combine it. Split, then solve it, then combine it. So, but here one thing you should understand that sorting list is there and we are returning that counting inversions also. So we do the sorting job and as well as that counting of inversions also. So the counting of inversions, so while you do the merging it, So we are doing the counting out. How many inversions are there? We are trying to count it. And that counting of inversions, it says that if 2 inversions are there, so somewhat you are similar. Out of 5 movies, all 5 are different, like more than 5, you find it that you see that most dissimilar. So let me go for that where you can find it here. So there is implementation was there for this. So where you can see that here is the implementation. Yes, see, look at here, it is implementation. So first we do that inversion while merging is, it's very simple. If we add that IM from the R, so like from the R to the output means that IM is smaller than elements currently in the L. So each IM which is from the right position we are taking, see left position, left partition, and the right position is from the middle of the element to the last. Left position is from the starting of that one to the top of it, which is called middle or something like before middle. So if you add that IM from the R to the output, so IM is smaller than the elements of the L. So the whatever that left elements are there. So like you find that one inversion. If IM is, hence that IM is inverted in respect to that whatever left elements, like when you compare with right elements, we add that one increment to the count size. So we are adding one inversion, like, counting it. So please that here it is counting job is doing. See that here. So counting is increased. Counting is increased. So if you compare that equality, whenever equal elements are there, simply we are appending into the C. So like I is equal to the M at 2 different index positions. I is used it for that index position and J is used it for the index position. So because we are taking that A and B as a left partition and right partition, same thing is called again. Like merge and count is called. So if you see that next color implementation, so every time we change that left and right. So A is left partition and B is right partition. So in this case, we are doing that appending whenever equality is found, that B element we are adding. Whenever J is equal to the N, we are appending that A from the left partition. For example, you find that so A is less than that B. So what exactly is that left partition element, which is less than that right partition element? So we are appending that that A of I, which is the left partition one first. Because if you see that the order of sorted, already the prof has been given like 2, 3, and 7 is there here. So you find that 1, something like 6 and 8 is there. So while you are getting the 1, we are getting it is 1 is getting, while you are adding 2 is okay. Whenever you are adding 6, so you might have to cross it. In this crossing, you can find it. This is what exactly is. So whenever smaller element is there in this one is not a problem. Whenever you find it is greater element is there, so this has to be achieved first. So that's the reason there is inversion is found. So this inversion has been counted here. This is what the count is increased. So these inversions are increased in the count, and we return the sorted C, which is the C is sorted, and along with that, count also increased. The count is increased, which is called inversion. So the conversion is happened if and only so that A of I is greater than P of J. So this is called right partition. So whenever left partition is having bigger value than that right partition. So this one is called in the next. See, look at here. See that here it is the merge and count is sending 2 halves. See, first half we already got it into that left. Second half already we got it into that right. Along with 3 counting we got it. So left, right, and then we are getting that counting of B also. See, every time we are calling it is with the left and right. So where that left and right is, we are getting the left top, that is 0 to off time, which is off of the list. And here it is right is that half to end of the list. So every time the recursion is called, this recursion is calling sort and count, and this each sort and count call is calling that merge and count, what is left and right partitions is sending. So each left and right partition splitted one. So in that it tries to find out that inversions also. This is the inversions count. So count of the left, count of the right, and count of the wherever the inversions are found. So this is what is happening. See, sort count is a merge sort, which it is calling that merge and count. So which is internally it is calling merge and count. This merge and count job is that sort and count the inversions. So this sort and count job is that sending the left partition and right partition every time. So divide, every time divide job it's doing, and solutions are merged by the conquer. This is the conquer job is done. So this is about that counting inversions. If you see the recurrence relation, which is similar to, so whatever, yeah, here it is. So here that inversions are still, it is ranging from O of n square only, because 2 times n by 2 plus n time, when you are doing this, it is one element is there. So we don't have that any kind of further inversions. Only one element is called, it is constant. So at that time, one only. Whenever n element is there, 2 times n by 2 is n. So T of n, to solve it, we require that n log n. So here the number of inversions still, it can be, you can find it that number of inversions by doing that n square only, so that it is ranging from 0 to n into n minus 1. So actually enumeration, we are not using enumeration. Actually, if you use enumeration, that's a different kind of concept where it is without inversion, without enumeration only we did it. But it is, if it is enumerations are used, maybe efficiency can be improved. So enumeration is a different kind of concept where that in this particular course, they did not refer that enumeration of it. So this is 8.1, the first additional problem. They solved using the divide and conquer. So hope you have been understood. So shall we go for the next? Yeah, just give me 1 minute and drink the water and come back. Yeah. This is 8.1. Any particular issues about any clarifications about 8.1? Yeah. So we'll proceed for that 8.2. It is closest pair. It's another problem which they were trying to solve it using divide and conquer. So let me see that where it is, that first phase of. Yeah, here it is. So actually this particular problem earlier we have seen it, like in the beginning of complexities, we want to analyze it. So you have a screen and we are playing the video game. There are a lot of gaming objects are available. Of course, some of them are enemies and some of them are survivals where we want to escape from the enemies. So we want to find out that the closest pair of objects, and based on the closest pair of objects, we do the action, whether it is coming one doesn't hurt it. Some kind of video functionality, we don't know what it is. So whenever you want to find out that closest pair, definitely each of the object is having x coordinate and y coordinate. And another object is also having x coordinate and y coordinate. So we want to find out that, so it might be point A and it might be point B. So the point contains that x and y coordinates. So let me consider each of the object is a one point, which is located with xy coordinate. So we want to find out that whether that PA and the PB has been located in a shorter distance or not. So maybe you have a PC is there, another point PC, another object. So which is nearer between A and B or A and C or B and C, which will be then nearer. So such kind of thing, like the closest objects, if you want to find out the closest object, we want to compute the distance. So the naive approach already it said that is n square. And clever algorithm is simple. We will sort the points, and then we want to find out it, which already we have discussed it, like in the earlier, whenever complexity lecture by the prof, he said it is to find out the closest pair of it, it requires definitely that 16 seconds of time for deciding a closest pair. So instead of it, if you have been sorted and doing it, quickly you can find out which is the closest object is then. So for this, we can apply the divide and conquer also. For this particular problem also, we can apply the divide and conquer. So that's what this particular problem, what really it is, recalling the video game. Earlier in the analysis of that algorithms beginning session by the prof, it has discussed. So let me see that what really point means. So he has given that sequence of things about point. Yeah, this is the point. The point is simple. So it has that x and y coordinate, x position and y position. Every point is available. So let's, already we said it is a point 1 and point 2 is there. The distance between these 2 points, like D, you want to find out the D. So there is a Euclidean distance formula, like y2 minus y1. The y coordinate of the point 2 minus y coordinate of the point 1, the whole square, plus x2 minus x1 whole square. So that square root of it, we can get it the distance. So here given n point, P1, P2, Pn, find the closest one. So assume that no 2 points have that same x and y. So like already in the video game, they said it is, they are at different location. So we are not assuming that both of them are available on the same location. We are doing such a way. If any kind of such thing is there, rotation has been done slightly, like the degree position has been changed so that they are in different locations. Of course, we don't consider this if both of them are in the same. If both of them are in the same, so at that time we rotate, that is not considered, or algorithm is modified slightly, but that is not considered in this lecture. Only thing is assume that, so x or y coordinate 2 points, no 2 points will share that same x or same y coordinate. So here brute force effort is that we are calculating the distance, like distance between these two, distance between these two, distance between these two, and distance between these two, and distance between these two and these two. Also we are calculating. That is called a brute force or naive approach. So definitely it requires that O of n square. This is simple traditional approach which we do that. Each pair of points, we try to calculate the distance, so that we call it as distance of each pair of Pi and Pj. So all points of x positions, all points y positions, we try to calculate the distance. This is simple brute force. So let me go for, they are finding the closest pair using the divide and conquer. So there are 2 ways in the lecture. They said it is 1-dimensional and 2-dimensional. So let me see that the 2 ways of finding closest pair. Here is see. So here that 1-dimensional solution, he referred it. So that's what exactly here is 1-dimensional solution is. So x1, x2, x3, all these points are arranged in the 1-dimensional, like, so x1, y1, and this is 1 point. It includes the 2 coordinates. And another point is there, which is also having x1, y1. And another point is there. So it is also having x1, y1. So all these are arranged in a single dimension. That's called 1-dimensional of points. So each particular x1, x2 is 1 point. So all these are arranged like side by side. We sort them. So using xy coordinates. So whenever sorted points are there, the nearest finding is very simple. How it is simple is, see, look at, if it is sorted in ascending order, so we have that points are like this. So all points are arranged in increment order. So don't think it is increment, even it's a descending also, no problem. For example, this point is there. I want to find out that that's the nearest point, nearest object for the P. So what simply I need to check it is, I need to compare with P plus 1 and P minus 1. The reason is, others are definitely far away from P because they are already sorted. I hope you understand. Fine. So that's the reason, if it is sorted, I need to compare P with P plus 1 and P with P minus 1. So out of this, which is the shortest object, which is the shortest and closest pair of objects, whether P and P plus 1 is closest or P minus 1, because adjacent elements only we compare. This is one-dimensional solution. All points are arranged in sorting order. For the sorting, we required that it is n log n. And for the scanning, we required that each point we take it. From the point, we take that adjacent points only, left adjacent and right adjacent. So by that, we can say which point is closest for the P. And if it is two-dimensional, so whenever you take two-dimensional, we are applying the divide and conquer, split the points into two halves, like all points are arranged. So we are trying to divide them into two halves. So the left part and right part. Recursively, we try to find out the closest pair in this half. For example, this is first half, this is second half. We try to find out how many points are closest here, which is the shortest, closest pair here. And we are trying to find out which are, definitely one of them is closest. Maybe this to this or this to this, this to this. We try to find out it. After finding the closest pair in the each half part of each partition, and we try to check that distance between that across these two halves, like across these boundaries. So that is, across this line. What do you call, here it is across this line. So how to do this one is efficiently. So whenever you have two-dimensional data, if it is one-dimensional data is okay. Whenever two-dimensional data is there, how to do that closest pair finding. So that is a simple introduction about this closest pair. So let me see that dividing points, the job of the dividing points. So which has been started, this one. Yes, here is the place. The next place is not. Yeah, here is the place. See, look at it. So given n points, P, P1, P2, Pn. So where Px, P sorted by x coordinate, and Py, it is sorted by y coordinate. So what really it is, first it will sort by the x coordinate, and then it will sort by the y coordinate also. So now what they do is, they are trying to divide it into two halves. This is the left partition and right partition. Left half and right half. So by a vertical one. So here what they do is, how to compute Qx, Qy, Rx, Ry, it's efficiently. So Qx is the first half. So it is first half of Px, first half is. Rx is the second half, which is right one. So let's xr be the smallest x coordinate in R. So smallest x coordinate. So which is out of this, which is the smallest one. P is in the Py if the x coordinate in P less than the xr. See, look at P is at one of the point, it might be somewhere else. If x coordinate of P less than that xr, one of them is in x. So what really it is, one of them is smaller, definitely we shift it to qy. Otherwise, you leave it to here in the ry only. So here x coordinate we compare, like x coordinate we compare, then the xr. So move p to that qy, and then otherwise it left in that ry only. So all of this partitioning will be done in this O of in n complexity only. So really each point is compared with others. So each point of x coordinate of the p is compared with that xr, like right side object, we compare it. Whether you want to send it to the left partition or you leave it for the right partition only, we compare and we do the two halves. After doing two halves, we try to find out the closest pair. The closest pair finding is we are applying the Euclidean distance. So here is the closest pair. So see, look at that closest pairs in the two-dimensional. We take that px and py. So point of x's and point of y's, both of them are two different lists we are taking. So points of all x coordinates, we are taking a list of it, and we are taking that list of y coordinate also. So we split them, like qx and qy is one split, rx and ry is one split. Now we recursively find it, the shortest distance you can find here in this shortest pair. In this also shortest pair. So here, shortest pair. Recursion call is twice it is done. So two recursion calls. Two calls have been done. So one with left part, one with right part. So in this case, if you're finding it, maybe you find one of the closest pair is this, maybe one of the closest pair is this. So now we try to combine these solutions. We try to combine it. Once you find it that two closest pairs, we try to combine. So when you are trying to combine it, you try to check it another shortest distance across these boundaries. For that combining, there is a combining which is efficiently they are trying to combine. See, look at here. Yeah. So whatever we said it is right. The shortest one is dq here. The shortest one is dr here. We found that dq and dr are the closest pair of points which you find in the two different partitions. So in this, we are trying to combine them. How to combine them is, there is lambda. Yeah, here it is lambda expression. See, look at it. Out of these two, we are trying to find the minimum one. dq is, and compare with dr. Out of this, which one is minimum? Definitely we can say that dr is the minimum, because you find it is smaller distance is this. This smaller distance is considered as a lambda. Maybe one pair is there in the right partition, one pair in the left partition, that is closest pair. Comparatively left and right, which one is the smaller? That is considered as a lambda. And using that lambda, we are trying to make a band. See, look at this band is width is definitely size of the lambda. See, look at here, this one. So in this lambda, we are trying to find out. So no pair outside this band can be closer than the lambda. See, look at out of this particular one, beyond this one, so can be closer to that lambda is. So using the lambda, we are trying to find out that intersection. See, look at the combining solutions. So we try to go for combining solutions, how they are combining. Here that lambda is, again, we are making it is off of the lambda, so that no particular point is here it is. Yeah. See, look at. So divide that lambda band into boxes, which is off. So one lambda, if you have been divided, like height and width, if you divide it by 2, so you can find half lambda of it. And similar way, this height also of lambda. This complete lambda is going to be 2 halves, and width and height, both of them is divided, so that it is going to be divided into 4 halves, so that it looks like a box with diagonal. It is completely diagonal, which you can find it 4 sides of it. So any point, lambda must be lie in the 4x4 neighborhood box only. So you can find it only 1 point. We don't find more than 1 point within this lambda. So that's a sure, that's happened. So in this, we try to find out from qy and ry, extract sy, point in the lambda band sorted by y, so that we try to find out that which one is the smaller distance. Comparatively, this y and this y is shorter, and comparatively this one and this one, which is the shorter. So which one is the shorter, that is going to be combined. So which is called linear scanning. Linear scanning is always bottom to top. So linear scan is bottom to top. Bottom to top. So when you do that linear scanning is bottom to top, we try to change that y coordinate only. We try to check that y coordinate only. So because y coordinate only, it is. So this is y axis. This is x axis. So x axis, they are same. We are trying to scan it from the bottom up, so that called linear scanning. So we are trying to find out the next 15 points which will be the closer for this point. So if any of them you find it's closer, we try to make it is a closest pair across the boundaries. So in this way, it is going for the pseudocode. So he has given pseudocode only with analysis. Yeah, here is pseudocode and complete analysis. See, look at in this pseudocode, what he wants to tell you is, if Px is having only 3 points, 3 points means we have a point A, point B, and point C. So what you do is you compare A with B and B with C. B with C, whether B and C is a smaller distance, and A with C. So within 3 comparisons we can, so that compute pairwise distance. Pairwise distance means AB, whether their distances we are finding, then B and C we compare. So which is the shorter distance, we try to find out it. And then whatever distance we got it, again we compare A with C, whether it is shortest. Whatever that AB combination, BC and AC, which is the shortest distance, that one we get it. If it is less than or equal to 3 pairs. 1 pair is there means simply we return one distance only. If 2 pairs is there, simply if and then do it. If 3 pairs is there, we do that if and else if. Whenever we go to that more than 3, at that time what you do is, we are constructing 2 halves. Like left partition we are constructing, right partition, by comparing sorting. Like left coordinates and right, sorry, x coordinate and y coordinate of Q, and x coordinate and y coordinate. First we compare that x coordinate, then by y coordinate. After that, we try to find out closest pair in the offs. Closest pair in L, left. Similar way, closest pair in R. So that we try to find out, like this one. See, here it is. The closest pairs in the each off. Here is. Yes. This is the closest pair of points in the Q partition, closest pair of points in the R partition. So after that, closest pairs in the partition has been done. Each partition has been done. So then what you do is, we are trying to scan it, finding that across points we try to find out it. So then across points we are trying to scan it from the bottom up. So after that, when we are finding out it, so we try to find out it, scan it, then return that Q1, Q2 and distance of Q1, sorry, distance of Q points, R1, R2 and QR. And similar way, across boundaries, we try to find out that S1 point, S2 point with the distance of S. So which is the closest. So this is, it is written like DQ is the minimum one in the first partition. DR is the minimum distance in that right partition. And DSC is that minimum distance in across the boundaries. So that is what is happening. So here were the sorting of points, we required n log n, and the recursion, whenever you do the constructing the left partition and right partition. So in this case, we required that O of n and O of n, and scanning from the bottom, the each point it is bottom to top, we required O of n, And the med sort, which you already know, the 2 times n by 2 plus O of n. So which is that any of them, like sorting, recursion of that, each of that. So he required that O of n. So overall is that n log n. So this is about the closest pair. So where it is 2-dimensional, if it is 1-dimensional, it is pretty easy. Like you sort them and you try to compare only adjacent elements. So whenever 2-dimensional points has been given, so we try to split it like left and right partition, then shortest pair in left partition, shortest pair in right partition, then shortest pairs across boundaries. So that is going to be ordered. Like out of which again these 3 is there, in that 3, which is the smallest one, that is ordered first. So you can find out the shortest distance of pairs. So which is the closest pair of objects. So this is 8.2. So please ask me for any clarifications.
So scanning takes big of n.
Yeah. Yeah,
Like,
it is. See, look at. Yeah, here.
we
See,
have
from the bottom we are coming.
we have
From the
doing-
bottom we are coming.
but
Clear?
we are checking only 15 blocks, right?
Yeah,
So
15
it
only.
should be
15 only.
less.
Yes, yes. See, look at. So this is 1 point. Clear?
Yeah.
This is 1 point. No, there is no chance of any point around it. Is it right? In this particular box, you don't have another point. Am I right?
Yes.
So similar way, in this only we have only 1 point.
Yes.
So that we start so this comparison we do it across this one. So this one maximum, clear? And so any of that, like you try to compare off lambda. No, off lambda means 16 comparisons only maximum. Like so we are comparing each point with the next 15 points only. Like across boundaries. What do you know? You are scanning from the bottom up. Across boundaries, still you can find it another points at bottom actually. So each of them is available with 4 and 4, 16. No, wait. 4 is there, 4, 8. Another 2 more is missing. Actually, in the diagram, you can find it with full view, or where you can find it another still more. I hope you understand. This box is having 1, this box is having 1. Similar way, you have that another box is there, another point is there, and you have another point is there. Like, I hope you understand. So this point is compared with another maximum, another 15 points. Similar with this point is compared with another 15 points across the boundaries. Clear? That is what happening. See, look at, yeah, here it is. Scan SY from the bottom to top, comparing each point with the next 15 points in SY. So in this particular strap only, in this particular band only, it will compare. Because already this band is framed with minimum distance. We try to compare only within this band. So within this band, you can find maximum another 15 points only. So because each of them has been divided into 4 halves of lambdas. Clear? It is 16. So that it is current point, if you consider it is 15 comparison zone.
So can you point out the
Yes.
15, can you point out the 15 boxes?
Yeah, it is. See, here it is. If this point is taken, this 4 boxes is there, another 4, 8 is there. Still, if this point is considered, see, this point means this completely 1, 4 boxes. Clear? Okay, this point in this case 1, 4 boxes, and another 4 boxes. Okay.
Okay.
So
And the-
again,
and
if you go
and
for
left,
down,
on the left side is 4 boxes, is there, no, sir?
no, 1 point. 1 point we compare. 1 point we can compare with another right side elements, no?
Oh, okay.
Because across boundaries.
Okay.
So even another bottom, if you compare another 4 boxes, you can find it. This SC is for across boundaries. Across boundaries, shortest pair. Bottom up we are scanning.
Okay.
So across boundaries means like the
Closest,
line.
closest means this distance.
The across
distance.
boundaries means, yeah.
Across boundary means this left partition is Q, and right partition is there R, no? Clear?
So, okay,
Means,
one point is in L and one
yes,
point is.
maybe you find it a smaller distance of point, which might be still smaller than this particular point. Okay.
No,
Comparatively, you find it one shortest pair is here, which might be shortest pair 1. This is shortest pair 1 in R exclusively. That is what shortest pair we are finding it. See, shortest pair of each particular points we are finding. See, here it is. First we find it.
is
Yeah,
it not
here
enough
it is.
if we compare with the 8 boxes?
No. See, 8 boxes is not. First we are finding it is minimum distance of this point and minimum distance of it. Out of these two, which is the minimum one, that is taken as a band. The band is this lambda. So that lambda is divided into 4 halves of lambda. That side and height. So width and height. Fine. So if you take one point, there is no other point in the same particular left. Definitely there is no chance. Clear? Because already we found that lambda is a minimum one. Lambda is a minimum one. Minimum means in the minimum distance you don't find it. So other partition only you have to check it. In the other partition, maybe you find it 1 point, any of these 4, like above 4, above this, equal to the 4 boxes, or bottom of it, or another bottom of it. Maximum 15. Like this point is compared with only another 15 only. Clear? Bottom up, scanning from the bottom up. This is combining solutions. Splitting the solutions is already done. This is already splitting, divided is done. Dividing and then finding the sorted and shortest distance, we found it. And across boundaries means whatever you are combining. We try to combine it, no? This is the part, yes. This is the part, scanning. Scanning from bottom up. That is finding S1, S2. That is called shortest distance across boundaries. S1 is a point in the left partition. S2 is a point which is in the right partition. We try to find out a distance which is called ds, which is the shortest distance. Fine. Which is called bottom up. So constructing the shortest distance, it requires another O of n. Another O of n. That's the reason recurrence relation is merge sort along with O plus n, so that it is ultimately, they said it is n log n, overall complexities, because highest one taken for the sorting. So that's
Why-
taken is,
Sir, why we are not calculating horizontally? Why only bottom to top?
yes. So because horizontally it's already distance is calculated. See, horizontally this Q partition, R partition, the horizontal between X and X is already done. Is it right? These points are already done. Fine. These points are internal partitions distance already done. We got one distance. One distance is like nothing but dq. Another distance we got dr. Now out of these two, again minimum is taken. The minimum one has been created one strap. In this strap, any minimum distance you find less than this, that is considered as a ds. So yeah, ds, they are considered as a ds. dq, dr, ds. All these three we are returning. Like dq we are returning, dr we are returning, ds we are returning. All of them are minimums. Fine. So these minimums are returned. Tell me.
No, this ds may be horizontally also shortest distance, no, sir?
Yes. See, dq, dr are in the partition only, in the sub problem. But whenever it's merging, you require across boundaries, no?
Okay, across
See,
boundaries.
look at, look, across boundaries. See, very simple. This list is there. Let's we consider this is a Q list. This is a R list. Fine. So inside the boundaries, it's already sorted. Let's we consider 7, 8, 9, 10. This is also internally sorted. Like you are having 3, 11, 12, 13. Fine.
Okay.
Now we try to do that merging job. For the merging, we try to scan up bottom up. So when you do the bottom up, out of these two, minimum 1 is taken. So the 3 is taken. After the 3, we try to check it. Anything is just above 3? No. Anything above, you find it, so 7. So 7 is merged. Fine.
Okay.
So now that across boundaries, we try to merge it the shortest distances. So the 3 is joined, 7 is joined, then again 8 is joined, which is from this partition only because Q is considered. 9 is also taken from this partition only. After that, 11 is taken from this partition. 12 is taken from this partition. Sorry, 9 after 10 is also taken. 10, 11, 12, 13 is taken from this partition.
Okay.
So that each point we are taking minimum 1. From that minimum, we try to check it whatever to be merged, like it is splitted. Sorry, splitting is done, merged. When you joined it, we try to join it efficiently. Shorter one, we take it the shortest one. From the shortest one, we try to add the points and keep on adding them so that we get it. So the pairs which is arranged in the shortest distance, like DQ smallest list, DR smallest list, and DS smallest list. DS smallest means across boundaries also we get the shortest distance. 3 minimums we get it, depending on which of the DQ, DR, and DS. 3 minimums. Fine. So this is about that. Yeah, here it is. So the overall complexity is n log n only because the sorting is taken n log n. And constructing separate shortest distance is n because n number of scannings only we do that shortest distance in Q partition and shortest distance in R partition. And constructing shortest distance across boundaries, these boundaries, it is also here it is. And scanning, we do that SY from the O to N, like bottom up, we do the scanning. So that's required, that O of N. So the recurrence relation is 2 times n by 2. Why it is 2 times is that 2 partitions every time the problem is splitted into 2 partitions plus O of n, like merge sort only. Overall is that n log n. This is about that 8.2. Second problem, which is called shortest distance. Give me one time. Yeah, this is the third problem. So this is most traditional multiplication we do it generally. So in the case of divide and conquer approach, whatever that traditional naive approach we do that, in the divide and conquer also same kind of thing is, but a small kind of variation in the time complexity, which is that a new what exactly that one particular author has been given one algorithm, Karatsuba. So by that we can reduce very little complexity, like performance is increased little bit. So let me see that what real is. Yeah, here it is going with first, it is basic example. Yeah, here it is. See, look at any of the multiplication we do it. So definitely we do the digit by digit whenever multiple digits are there. If you consider that Multiple digits means here 2 digits are there. Here it is 4 digits. So don't worry about that, whether it is binary number or it might be the decimal. It might be decimal this. It's a binary one. So it's not an issue then. So whenever you do the multiplication, we do that partial product of it. So if you think about partial product, this is partial product 1, partial product 2. So we do that partial product 1 and partial product, the product 1 and product 2, these two things we do that addition. We can say that, so partial adding of it. So adding up all of the partial products. So that is simply works. Same strategy is applied for binary also, same thing like if it is. But here the number of partial products are increased. So because of the number of digits. So here the partial products are 4, P3 and P4. So of course, 4 times we add it every time the partial product is calculated. We try to add it into another variable. It might be that, so adding of the partial products is. So here it is, whenever n bits of numbers are there, let's we consider the binary number, because binary number considering they have taken even in the complete application. N number of bits are there, definitely n number of partial products are there. 4 bits are there, so that 4 partial products. That's what it is said. So adding each partial product cumulative, it is sum of that O of n, and overall is that n square, because we do the multiplication. Like we take this unit place 1, we try to multiply all of the digits of the first number. We take the tens one, like this part. Again, we try to multiply and again 1. So that's what it is happening. So in this case, we say that each partial product is again cumulative. It is sum operation is just simply adding. Like it is 4 means 4 sums you do it. But the multiplication operation, we do that each digit with other, all of the digits in the first number. So definitely it is n square. So it is, can it be improved? Frankly, then next divide and conquer policy we are applying is not improving. Same kind of complexity is carrying. But anyway, they want to apply the divide and conquer on this multiplication. How it is happening? Whether any improvement is happening in this one or not. So let's we see that. Here is the same. Yeah, we are going that similar kind of thing. Divide and conquer policy they are applying. To here. Here it is. Yeah, it might be last. Yes. See, all of them are put together. The 17th slide, yes. Yeah, 17th slide. 17, okay, great. Maybe 18th, what is there? Okay, so you're rewriting Karatsuma. Yeah. So here what they did is that they are taking that off of the bits. Like if it is 4-bit value is there, we try to divide into 2 parts. Even you take the 6-bit value or 8-bit value. Even it is 5-bit value, also 2 halves. But only thing is, this is unit place. And it's going to be the higher place, which is called, you know, if it is 2-bit value, unit place is there, tens is here. If it is 3-bit value is there, unit place is here, 100 place is here is available. So it is n minus 1 to n by 2, which is that left part is having the bits of that higher bit value. And this is called unit place. Similar way, here 2 groups is there. 2 groups have been divided. First group is there, second group is there. Same number. It's divided into the 2 parts, you know. Sorry, wait a minute. Yeah, it is 2 groups. Yeah, n by 2 for that first number and this one. Yeah, this is first number. This is second number. So here it is, you want to do that multiplication. If it is doing the multiplication, what you're supposed to do is, so each bit of this, we try to do the multiplication, each y0 with x1. Similar way, each y1 with x1, because 2 partitions it is. So then after it, across the boundaries it is, each particular bit of that x1 with y0, and then we try to do the multiplication across boundaries is, so y1 with x0. So here it is, we do that, it is 1 multiplication, this is 1, and this is 1, and this is 1. Total it is 4. So 4 times the multiplication is done. Like it is first half of that first number, and first half of the second number, and second half of the first number, and second half of the second number, and across the boundaries also. So when you are rewriting that x and y, you know, you are rewriting it as groups. So what do you say that this is the complete left part? So what do you say that this is the left part 1, and this is the right part 1, which you called it unit place. This is across boundaries, So this is 4 n/2 bit multiplications is done. So 4 times. So n/2 bits have been multiplication is done. So constant and standard time is the t of 1 is 1. And whenever more than 1 is there, 4 times n/2 plus n. So combining the partial products is there. It requires that O of n bits, which is called adding up, which is sum. So combining is sum, which is required. So this is the recurrence relation is been expanded format. So the overall complexity is not increased, which is that O of n square only. So even we use the divide and conquer, like first number 2 partitions, second number 2 partitions, and then after it we try to do that first partition of the first number and first partition of the second number, and the second partition of the first number and second partition of the second number, and then we do that multiplication across the boundaries. So even we do that 4 times that across multiplications. So the approach is not increasing that divide and conquer policy, similar kind of complexity. So this one has been rewritten by the Karatsuba, which is that another algorithm has been introduced by the mathematician Karatsuba. So which has been given a complete expansion format. He has been rewritten. Yes, here is them. Karatsuba has been rewritten. Complete rewritten. It's here, yeah. Yes, here it is. Yes. See, look at here. So what he is doing is, he is doing that divide and conquer is not helped. So what you do is, we subtract. So once the multiplication is done, we subtract. See, look at, this is okay. This is a constant time whenever only 1 bit is available. Like we have that n is that only 1 bit. So whenever you are having that size of that n is more than 1, we do the 2 partitions like m. So in this, what it is doing is bit shifting they are doing. So bit shifting is simple. So this is a full part of a bit number. Like if you take about that 327, so we try to do that, divide by 10. So we get 32. Once you get 32, we drop this 7. We drop this 7. So right part is going to be, the unit place part is dropped. Similar way, same thing is happened for the second number also. This is the first number, the number 1, number 2. So we get the 2 halves. So then we do that, the fast multiplication of that, whatever I said it, you know, the first half part of this first number and the first half part of the second number. And second half means this is the left part, what you call unit place. So we do the same. After that, what you do, the remaining part of it. See here that remaining part is calculated. Remaining part. So whenever you do the remaining part, you know, so x1 minus x0 it's been done. Y1 minus y0 has been done. So because already y0 is already participated. So remaining part of x1 and y0 is already participated, remaining part in the y1. These two we are getting. That's called A and B, the remaining part. So once the 7 is excluded, the remaining part. The 2 is excluded, the remaining part is 3. So that is doing the third multiplication. So that 3 multiplications we do it. So whenever you do the 3 multiplications, so this is the C, look at here. P and Q are that 1 and 1, 1 and 1. So this part is 1. So what do you call, across boundaries? Across boundaries are after subtracting. After subtracting. So the subtracting is done by using bit shifting. The bit shifting is simple. So we are getting that division value or divide value, and we are getting the mod also. So remainder. So 2 operations they are doing. Like they are subtracting x0. X0 is getting that remainder. X1 is getting that 32, which is called extracted value. So that is what is happening. So by this, the Karatsuba has been said it only we required 3 into O of n by 2 bit multiplications only. We don't need 4. So one more time, we don't need to do it. Already multiplied things we can be subtracted. So that is what the Karatsuba has done. Actually, Karatsuba has said about that addition, but that has been defined in a different way with either other. So please look at that. There is historical thing is there. There is historical reference. This is complete analysis. Here is the analysis. 37. Here the 39 is analysis standards. Yeah, here it is. So complete recurrence relation is here. So where the T of n is taken, which is the expanded format, 3 times n by 2 plus n is been written in expanded format. When it comes to the log conversion, so finally we got that n log 3, which is n log 3 is less than value, which is n square less than. So we say that n to the power of 1.59 somewhat less than that n square. So which is somewhat less than this n square. So because we do that 3 times multiplication only after subtracting that multiplied parts. So whichever have been already multiplied and added, they subtracted, and remaining parts only we do that 1 multiplication only. So actually this is a historical note has been given by the prof. So here is, yeah. Here is that one more historical truth.
Can you show the dry run for this? I didn't get much.
What do you want to do it?
Like example for bit manipulation.
See, bit manipulation. See, 4 bits you have taken. This is one number. Another number is taken, like 1, 1, 1, 0, something like this. So these 2 multiplications you want to do means first basically we have to do the 2 halves. So 2 halves means first we do that. 2 halves is been done with 2 partitions, like x partitions and y partitions. So please look at back the x partition and y partition. So this is we divide into 2 parts. This is x1. If you see that this is x1, this is x0, this is x0. So what do you say that x1 and x0 is second of, this is 1, 1, this is 0, 1. Clear? So then after it, second number is there. Second number is going to be again doing the 2 parts, that is y1, y0. So y1, y0 if you consider, so y1 is going to be the 1, 1 and this is 1, 0. Fine. So then
Yes,
first what you do is divide and conquer. See, actually divide and conquer means again this is going to be splitted. Again it is divided into 1 part. So one part is divided. First these 2 are multiplied, like 0 and 1. Then 0 and 0. After that 1 and 1. 1 and 0. Am I right? So that here it is the multiplication of this is 1 time. Here because again smaller parts it is divided, of course. Again this multiplication is 1 time. So after that across boundaries is done. So across boundaries means x1, sorry, this is x1, x0, no? Yeah, here. Because why they said it's x0 is unit place is smaller. Unit place is at right side. That's the reason they said it is x0 and y0. So here, across boundaries, they do it. Whatever that we got it, the result here, these results are again multiplied across boundaries. So totally it requires that 4 times. Another time here, another time here. So it requires 4 times. That is divide and conquer policy we applied. But even that, the complexity is n square only. Clear? The complexity is n square. Because if 4 bits are there, the size of the 4 bits of numbers, we try to do that each bit with other remaining 4 bits. Am I right? Like 0 is multiplying all these 4 bits. 1 is multiplying all these 4 bits. Again, 1 is multiplying all with 4. This one is multiplying with all 4. Is it right?
Yes, sir.
So this is what exactly is happening. Divide and conquer, even you applied also n square only. For example, Karatsuba said it. What he said it is, so instead of again you are multiplying these like across boundaries. So what he did is, see, look at this part. We required across boundaries. When you are getting, we are doing the remaining part only. Remaining part is subtracting. This is, see, the bit shifting we do it. The splitting of part we do it without without including. See, whatever the multiplied value is there, that is subtracted. See, this x0, y0, from the x1 they subtracted, remaining value we get it a. So y0 is subtracted from y1, remaining value it's there. Like if you think about this case, see, look at it. See, we are subtracting y0 from y1. So whatever y0 is already participated in this particular multiplication, we subtract remaining part only, we take it from y1. Again, we don't give the participation of y0. Similar way, x0 is already participated in this multiplication. We subtract remaining part of x1 only, we take it. So that if you do that remaining part means only one multiplication is there. So this is inside of it, 1, 1. And across boundaries, we have only 1. Because after subtraction, whatever participated things have been subtracted, remaining part only there. So that it is totally 3 only. 3 times only we do that divide and conquer. So this 3 times means, so this is log 3. Log 3 means n to the power of 1.59, which is not much better than n square, but somewhat it's not reaching that n square. So that is what you are doing subtraction. Actually, Karatsuba doesn't mention about the addition, subtraction. He said about addition only. See, look at, he said it is addition only. But addition, what it is, it is creating additional carry, like adding of 2 bits or adding of 2 numbers, it will generate another carry. This carry again, you have to use it for further sum, further addition. So to avoid it, so one more mathematician, computer analyst has been said it. Donald Knuth has been said it. So instead of using addition, you do subtraction, like x1 minus x0, y1 minus y0, because already y0 is and x0 is already participated with x1. Y0 is already participated with y1. So the remaining part of y1 is there and remaining part of x1 is there. They only multiply. So they only that across the boundaries they will multiply. So that time means that only one particular multiplication cycle. So that we get it simply, it is 1 point, which is less than so 1.59, which is lesser than the 2. That's what exactly. Subtraction they are doing. What exactly, remainder, dividing they are doing. So actually, even the professor lecture, he said about, if you could look at this one, about remainder and this, divide and this one. If you have taken that one example of like 1053 has said it, one example. So when you do the dividing by 10, we get it 105. So of course 0.5 is there, 0.3 is there. That is excluded because with the 10 you do that integer division. After this, again 105 is there. In this 105, again you do the 10 because it is a recursion call. No, the fast multiply is called again with same number. So 105 again you do that 10 is getting, so that 5 is already gone. So every time the multiplied participated one is subtracted. So we get reduced one. Once you get reduced one, so the A and B also it is getting reduced if that subtraction already participated digit is removed. So you have the remaining part only. The remaining part means simply the multiplication part is reduced. So across boundaries you have only one multiplication only there. We don't have no two. That is. So you can see that lecture one more time. You can find it just that part exclusively, that remaining part where that n square it becomes that 1.59, which is square is reduced to n to the power of 1.59. But here one thing you should understand, actually Karatsuba said it is addition, but addition is returning carry forward. To avoid it, we go for that subtraction. So that remaining part is, so getting subtraction is no carry is generated, just only that remaining part is generated. Remaining part means definitely it is less than that existing size of digits. It's not increasing that carry forward value. That is simple. Okay, that's about it. So give me 1 minute. I'll drink the water. Yeah. Yeah, this is not a problem actually. It's a kind of representation. So divide and conquer is solved that many problems. Like earlier you seen that recommender system, the number of inversions we want to find out it. And we want to find out the closest pair. Even the inversions, we check that the permutations within the same particular list of recommendations, list of rankings. If you see about that nearest points you want to find out it, there also we have been used divide and conquer, like splitting of two parts and shorter distance between 2 points in each partition. And similarly, when you joining that solution, the problems, sub problems, you want to join it, at that time also we are trying to find out that minimum distance by using the lambda, which is where you can find it the shortest distance. Out of that left shortest one, right shortest one, and across the boundaries, which is the shortest one, we try to take the 3 minimums. And when you think about that multiplication also, it is not much difference if it is multiplication. So always it is n square. Even you apply the divide and conquer also, we have that n square. But using the n square with subtracting already participated binary digits, or if you subtract it, so the remaining part is subtracted, the unit place is subtracted, whatever the unit is already participated, we can reduce it only by 1. Now all of these problems you want to represent it using the recursion trees. The recursion trees means, so what each level of recursion tree it is going to the depth. Sometimes it's going that expanded way. Sometimes it goes to the shrinking way. That's what that simple overview of this particular lecture. So let me go for this depth of this. So if you look at divide the recursion trees, so the prof has been said about that the types of this. Yeah, it is solving the occurrences. Yeah, here it is, different kind of recursions. Yeah, here it is. This is. See, already all of these 3 problems which you have been seen earlier. So it is using the dividing the problem into that smaller problems, shorter partitions, and solutions we are combining efficiently in the sense Across boundaries we are combining. Once you have been individually it is sorted, then we try to combine that across the boundary, so that final solution is going to be single. With solutions of sub problems, we combine that main problem. So the complexity is expressed. So now that recurrence relation of the complexity is expressed in T of the times of n. So let's we see that the searching and sorting. So the binary search, if you see that, so that is T of so the times of that n by 2 plus 1. So T of n is that so of log n. What exactly is that binary search? Because sorted one, we can say that efficient search. What do you call, efficient one? The list is already sorted. Every time we go for the mid position, no? So that's the reason it is. And when it comes to that merge sort, it is that n log n. So n log n is which is 2 times every time that off split is going. Split and sort. Split, sort, and merge. So first split, sort, and then merge. So after that, it is also that's n log n. And another divide and conquer, they have been applied on the multiplication of the integers. So the naive approach is already, it's n square. Correct subas you are applying is that log 3. So this complexities which you are representing, the times of n, you are representing T of n. Is there any way to represent that? So, diagrammatically you want to represent it. Is there any asymptotic expression like computation of the uniform way of representing of this asymptotic notation? So that's called recursion trees is there. So if you could look at the recursion trees complete slide. So what really the recursion tree is? The tree, how it looks like whenever you want to represent the recursion tree, even it is factorial. Yeah, here it is. All of them are in sequence. Yeah, I hope it is this one, a complete slide. Yeah. So a recursion tree is a rooted tree, which might be one root is available. One root is available. So for each recursion problem, see, root is started with this, and sub of that sub problems also created. They are also called as the roots. Of course, it is root 1, root 2, and root 3. Sorry, it's how we use small one. Yeah. See this, that root 1 has been divided into again subroot. That's what the reason. Each sub problem again it is considered as one particular root element. Like this could be the main root of it, and subroots are created. So one thing you should understand that the value of the each node, see this particular value is what value it returns is, because in the terms of that T of n, because the recursion tree represents that the asymptotic notation or complexity required. So the value which is returned by the R1 and R2 and R3 is going to be that time spent, the time spent to compute or to do that work. And one more thing, please, it does not include the recursion call. Don't include the time for the recursion call. Please include that individual time required for to complete this job. This job to complete it, how much time it's required. That's called T of n is representing. So concretely, for the input size of n, which is called f of n, if it is one particular R1 is the one particular job, R2 is one job, R3 is one job. The value of R1, value of R2, value of R3 is a cumulative sum of the root. Like it's required the time complexity of 2, 3, and 3. The total time it's required for this one is the 8, because already 3 and 3 it's 2. So total root it's required is 8. And don't include that calling time. The recursion calls are not included. See, R is number of recursion calls, but it's not that, the time spent for the calling. It is number of recursion calls, number of sub problems. So each recursion call works on a sub problem is like n by c times, so that is number of sub problems, that is c of that works on the sub problem. Like recursion calls is the time spent is. So don't include that c is number of calls is. That's the reason. Recursion resulting recurrence is simple. The RT, so the time is spent for that each recursion call, that is n by c plus f of n. So that is recursion call of that each time has been the size of that n by c only, like it is divide and conquer what you are applying is. So the root recursion has a value of f of n, like each of them is f of n, like R1 is f of 1 and R2 also having f of n, R3 also f of having, and root also having f of n. Of course, this f of 1 is subdivided into the children. Each recursively is having that t of n by c. And listen, here each one is having level, like this is level 0, the level 0, this is level 1. And if you have again still subtree, you have level 2, because you might have again subdivision of problems. So you have that again. So one thing is each node at level D has f of n by c to the power of the d, c to the power of d, not it is n by c all to the power of d, c to the power of d. So assume for the simplicity that so n was a power of the c's. So that is simplicity what exactly, you know. So the number of that nodes are increasing. So that's what exactly is the representing is doing. So if you consider that one particular slide, here is, see, look at. So whenever level is increasing, see here, one recursion call is not included, just simply first time you are calling. So that complexity is simply f of n, this particular function. This it is getting 1, 2, 3, 4. So that 4 recursion calls are done. So 4 into each of that. See here that each of that f of n by c is calculated. So n by c is, and similarly still it's coming. This is what it is, you know, that is r, number of recursion calls, 4. When it comes to here, so r will become that 16. See, it is going for that. This r is going for another 4. This r is going for another 4. This r is going for another 4. This r is. So totally it is going for 16. So that's the reason r square into, so f of n by c square, and keep moving. So r is going to that r to the power of l, and f of n by c to the l. So whenever the level is increasing, the number of recursion calls are increasing, and at the same time the function outputs is increasing. Like each function, each sub function, sub problem is increasing. So that is what the cyclomatic complexity, it is calculated, it is represented using recursion trees. And if you go for that still further problems, it is only representing various problems how they are representing. Here it is. Here it is. Yeah, how this cumulative recursion relation is calculated. So when it is a simple kind of constant time of t of 1 is 1, we don't have that any kind of you know, sub problems are called. T of 1 is 1, so that because sub problems are not called. For example, t of 1 is n, that is t of n is there, like n is more than the 1. So at that time what happened, you know, you are calling sub problems, like you are calling that r to the power of I nodes. I is the level. So 0th level, first level, and second level. So whenever level is increasing, so you are having that r to the power of that, like r to the power of 1, you are going for r square. When third level you are going, that is, so the recursion calls are increasing, that is r cube, it is increasing. So the total cost, how it is calculated, you know, in the each level, so that is I to L, we are calculating that each recursion call, the sum of that each recursion call is calculated, and that is multiplied with, so f of n by c to the I. So this is the total cost, c to the I. So we are trying to do the complexity of each sub problem and added, which is some has been the addition of them because sigma symbol, all of them added up, that is 0 to L. So from the 0 to L, all these have been added. The total cost we are required. So in this case, if you go for that recall of that, the last term, when you say that leaf, what do you say? The last term is called leaf. The leaf is not having no further subproblems are there. So whenever you see that leaf is done, so the f of 1, which is r log cn, which is 1, which is simply base case. If you recall the the olden one, so a log bc is, which is similar to that, c log b to the power of a, which is c log a, which is similar to that, which is interchangeably we can use it, where a log bc can be rewritten like c log a. So whereas base is not changed, base is b. So that is what. And still, if you go for that, there are that examples has been given, like whatever that recursion examples has given, decreasing order, equal order, and increasing. Say, look at here. Yeah, here it is 3 kinds of recursion trees are there. So the decreasing order is there. So decreasing order is simple. So whenever you do that binary search, so the binary search is there. Every time we go to that n by 2. So the middle element we are trying to find out it. So n by 2 we are going means it is going that the solution is sinking. The solution is sinking. So that's called decreasing. Each term is a constant factor smaller than the previous term. So because the previous term is having size of 5, the next term is going that 2 only. The next term it is going 1. This is called sinking. The approach is called sinking. So that it is decreasing. Root is dominating the sum. So the root is having that higher, and sub elements are sub problems are having smaller. So root is dominating. Root is having higher asymptotic complexity than the sub elements. So all are equal also, it's there, asymptotically equal. Sometimes you have the increasing order also, exponential growth is there. So if you go for that exponential growth, so you have that naive multiplication, or it might be that Karat-Subhas one. So initially n is there, which is called expanded. It's not sinking, it's expanding. Initially n, so when it is going with 4 multiplications, n by 2, n by 2, n by 2, n by 2. So what is this n by 2, So this is leading place of it. This is unit place of this first number. And similar way, leading and unit place of the second number. So again, this has been splitted into that 4 parts. Like this is called n by 4, n by 4, n by 4. Similar way, this is also same, 4 parts. So this is exponential growth. Series growing exponentially. So each term constant factor larger than the previous term. So what really it is, leaves are dominating the root. So leaves are dominating the root. Here, in the case of this, root is dominating the leaves. So this is what the difference is. So examples also they said about it. So this is what simple kind of expansion. The merge sort is given one example. So merge sort is also one decreasing order. So and even it is a binary search also decreasing order. This is a decreasing order example. If you take the merge sort of 6 elements, here it is 3 elements, here it is 3. When it comes to here, maybe 1 element is here, 2 elements is here. 1 element is here, 2 elements is here. When it comes to here, no more because it's a leaf. When it comes to here, 1 and 1. So 1 and 1 is a base case, 1 is okay base case, 1 and 1. Here root is dominating the sub element, so that it is called sinking one. In decreasing part. So here they said it is 3 parts, decreasing example. Some of the recursion trees are in decreasing order. So if you go for merge sort, still complete expansion. Merge sort. Here it is. Quick sort also same. But whenever you think about this multiplication, see, look at here, it's increasing. So n by 2, n by 2, n by 2, n by 2. Again, this n by 2 is coming to that n by 4. N by 2 is n by 4. So it's keep on increasing order, so that it's going to be that increasing one. Exponentially, it is increasing. And this is what, yeah, even it is Karatsuba also exponential one, but only difference is 3 growth. So if you could look at that naive approach is 4, n by 4 is 4 times, n by 4 is 4 times, it's a 4 times. If it is Karatsubas is there, so we have only 3 kind of things. One is that unit place of the first number, leading space of the first number, this is called leading space, and this is unit place, and which is called across boundary. So this is what three times is. Again, this is going to be 3 parts, 1 and 2 and 3. It is also exponential growth, but it is exponential growth is that 3 times. Exponential growth is here, it is n to the power of 4. This is n cube, it is exponential growth is. So this is what the recurrence trees are helping you to represent that whether my recursion call is exponentially growing or decreasing, that you can find out it. That's only it is. It is not actually a new problem. Existing problem when you are representing with trees, how can you represent whether it is exponentially growing or it is decreasing or increasing. So that is what about this particular lecture. So I think it's not a new problem. Existing problems only they want to represent with asymptotic notation. Okay. Shall I go for the next? Yeah, just give me 1 minute. Yeah, this is the last one. Actually, quick select is just like quicksort, but quicksort is doing only the sorting job. But here what you do is sort and select the kth element in a fastest way. This is applicable for kth minimum or kth maximum. Whether the list is sorted in ascending or descending order only, it's a different. But it can be applied for either kth minimum and kth maximum. Let me understand what really this problem is. How can we solve with divide and conquer? There are similar slide. Yeah, okay. Yeah, here it is different. Here it is all are same. Yeah. See, look at. So how do you select generally? Let's we consider that we are not doing that any kind of divide and conquer. So how do you select the kth largest of list of elements are there? If you have that list of elements, like you have 17, 16, 21, 2, and 3. So which are unsorted list. Let's we consider that. So I want to find out kth largest, first largest, second largest, third largest, something like that. So in this case, it is much difficult to find the kth largest. So that what you do is, we try to sort the list. Once it is sorted, so your list might be in descending order or ascending order. Let me consider the descending order, because kth largest they asked you, so that better way is descending order. If they ask about kth smallest, we try to sort it in ascending order. So right now descending is the choice because they are asking the largest one. So 21, 17, 16, 3 and 2. So this list is already sorted. So we can easily find out it. Kth is nothing but first or second. If k is 1, simply we can find out that kth largest at this position. So second largest, k is 2 means second largest. So based on the k position, simply we can trace out it. So we can do the better. Like, can we do the better means what, k is 1 means, so maximum O of n. K is n means like nth largest you want to find out at that time also. So minimum we get it is O of n only. But any fixed k, we pass that simply we try to do that O of that k into n. K into n means the size of that list which is already sorted. So now any other case, like first largest, second largest, when the largest position k is increasing, like other than first is okay because maximum it is O of n. Whenever largest one is the last extreme largest, this is first one, this is the last one. Simply we can get it. First one is constant and this is okay, this is not a problem. But whenever other than 1 and other than n, so at that time what you need to pass it to the particular index, like second index, third index, fourth index. You're supposed to go for it. So what we do is we try to find out the median. So because if the list is a largest list is there, other than the first largest and other than the last largest, we try to find out some number of passes to find out that some particular k, so which is not first one, which is not last one. So at that time we don't find that constant time, constant and quickly you cannot find it. So what do you do that we go for divide and conquer policy. In that divide and conquer policy, what you do is we try to find out the median. If you see the median for this, let's see, it is a small list 5. If it is a bigger list of 1000 elements is there, we try to find out the median because already it is sorted. It's very easy to find out the median. So the median is that n by 2. So if you can find out the median in O of n, quicksort becomes that, so n log n. So that is what n log n. So already quicksort is having n square complexity whenever a bad pivot is selected. A bad pivot. So bad pivot in the sense you might select it either extreme left corner or extreme right corner pivot element if you select it. But all the cases I wanted quicksort, average case is this. So even you have that bad pivot or all cases, I want that n log n. Quicksort becomes that n log n for all cases. So how to do that one? That is called quick select. We want to do that. Quicksort is n log n complexity. By doing that median approach, finding that k as a median. So we try to do the median approach, getting the median, and that from that median we try to find out kth largest. So at that time it's very easy. See, recalling that quicksort, if you go to the recalling of the quicksort, there was a given, it is given with a slide, a complete slide with recursion strategy. Yeah, 9th and 10th is same. Yeah, here it is complete implementation is there. Here no implementation. That's all. Yeah, 10th one we can consider because it contains that implementation also. Yeah, look at it. So pivot partition sequence has lower and left corner and lower right corner. Sorry, upper one and lower one. Lower partition is definitely less than the pivot. So upper partition, which is already that. Here the pivot is going to be that kth one. See, look at the kth one. If you want to find out it, the kth largest element on sorted list. Even it is unsorted also, it will be sorted. Don't worry about it because we are doing quick sort and select kth minimum. See, if the k is less than m, m is nothing but the length of it. Our particular kth maximum is below that upper part, which is mean that lower part it's available. If that k is equal to the m plus 1, we got the pivot, right pivot we got it. If the k is available in the upper part, that k is greater than it, so then we search the right part. So which is called search here and search here. The same thing is happening. See, look at here. So this pivot when you compare with the left part is bigger and pivot is smaller. So whenever it's there, we are going for the upper part. Similar way, there is exchanging is done. We go to the lower part also. So that is what happening. So which is similar to that quicksort, going for the left part or upper part, lower part or upper part. We do that. This is same. And recursion calls is happening. So recursion calls is simply it is we are selecting lower part and k. We are selecting the pivot element, upper part and k minus m plus 1. So m plus 1 is that we are going to that upper part, which is mean that right side part we are going. So that is what exactly it is. But here the pivot is selecting with the median one. So pivot is nothing but kth position as median. Median only. This median is selected as pivot element. So they are not selecting extreme left and extreme right. So that the complexity in all the cases, it is n log n only. So let me go for that analysis part. Yeah. Yes. This is ended. Yes. Slide number 3. Yes. This is This is median of medians. So now this is we are trying to find out that recurrence similar to it. The worst case complexity, already we said it is extreme left and extreme right. If you select it, the pivot element, it's n square. If pivot element is within a fixed fraction in the sense we select that middle third elements. Middle third elements here it is middle third is simple. For example, you have 10 elements are there. 10 elements are there. These 10 elements we are dividing into the first quarter, second quarter, and third quarter. So what we do is we always select the pivot element at this place, second quarter only. So that's the reason. So pivot element is that middle third of values. Middle third of the values in the sense n by 3 plus 2n by 3. So what exactly is in this boundaries only? We don't select extreme right corner. We don't select extreme left corner. So at that time we do it, then only we get it n log n. So the worst case is as usual. So it is n square. This is happening even we are doing that kth maximum. So the complexity is not increased. So what we do is we try to do that median of medians. So one set of median is not enough. We try to do set of medians. Every sorted list, in that sublist, we try to do that again medians. So that's called median of medians. Yeah, here it is median of medians. Yeah, this is what the median of medians. See, what you do is, if that number of elements in the list is 5 or less than 5, we sort it, and we return that off of them. Off of them means that median is nothing but kth element. The kth element is considered as a median. Simply less than or equal to 5 means we return it. Otherwise, we construct it. What we construct is, we are trying to do that. See, 0 to length, but every time step of increment is 5. What is step of increment? You know, first time 0 to 4 is one particular range of values. Next time what happens, you know, immediately it will shift it to that I value to 5, because every time incrementation is 5. So 0, then plus 5. So it becomes that 5. Another 4 elements it will select. So that another 4 means it is going up to the 9. So after that, again from the 9, it goes to that, again from the 5, it goes to the 9th location. So 9 to, it's going to the 5, 14. So each of them is selected as one block with size of 5. Each block is selected. Whatever block is selected, that is sorted. Each block is selected and the block is sorted. Once block is sorted, now they are finding the median element. That median is added to list M. So it is constructing list of medians. Whatever that you have been given that size of more than 5 list, maybe 15 elements is there. These 15 elements have been divided into 3 blocks. So from the each block, it is extracting each median. So that is what recursively it is doing. So if you do that, look at here. Please compare it is column wise. Don't compare it is row wise. Column wise it's doing. So if you do the column wise, how many elements is there, in this particular list? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 elements list is there. So they try to divide it into that, each of them one block. So that is called 5 blocks. So, each of the block is having 5 elements. So in that 5 elements, they are trying to find out the median. That is called kth one. This entire medians are added to M, which is a separate list. So that's what each block is arranged in ascending order, top to bottom. So each block is. So block are in the middle. So block medians are in the middle. So 5 elements are sorted, 5 elements are sorted, 5 elements are sorted. So out of the 16 elements, they are taking each of them 5. So in that each of them, they are sorted and they are trying to find out the median of it. So that's called middle one. So once they find out the middle one, so it's very easy that here also see, here also 3 into length of L by 10 and 7 into length of L by 10. What exactly here also the same. The first quarter and third quarter, third quarter is avoided. This is avoided. This is avoided. This part is avoided. This part is avoided. So they try to compare. See, the medians of the median of the block medians is between this particular part only. Whatever this brown color part is there, this part only you can find it. Lies between, only in this part only it is light between. So if you look at this, locating the pivot for the quicksort, here it is median of medians have been called. See, look at here. Yeah, here is the median of medians is called. Yeah, median of medians is here it is called. See. So we check it that kth largest we are trying to find out it from the list L. From the list L, every time we are getting the half of them, that is called left partition and right partition. We can solve that lower partition and upper partition. What do you call this? Lower partition, upper partition. So we are finding that median of medians between that L to R. Find that MOM pivot and move it to that L. So pivot you are getting. So in that we are trying to find out the minimum one. So we try to find out the minimum one. So remaining partitioning part is same. So whatever quicksort code is there, same thing is repeated here. No difference here. But here that what do you call this fast select? What do you call, fast select is recalled. Here it is recursion call 1. Recursion 1. Another recursion call is called here. Recursion call. So by doing the recursion call here, every time we try to do that median of medians, we try to pick up that best pivot element, which is called kth one. So best pivot we are selecting in the middle element means we get it that the complexity is always we can say that n log n, because best pivot is selected. Best pivot is selected. So that pivot is selected using that k largest. So which you called, k largest is nothing but median of medians. So we can say that median of medians. In that median of medians, we try to find out that kth largest one. So this is the summary of it. Yeah, what you call it is fast select. Yeah, it is combined, put together. See, median of median, it helps you to finding the good pivot, which is complexity of O of n. Selection becomes O of n. Quicksort will become n log n. Notice that the fast select with k, that is called, every time we try to find out that k is nothing but the median of medians on time of that O of n, so that it is the quicksort will become all the cases. Even any case, it is n log n only. That's the reason we can say that it is fast select sort. Other than the quick selection, we can say that fast selection. So this is historical truth which has been introduced, that quick select over that quicksort. Quicksort having one particular, if you select a bad pivot, it is a problem. But quick select is always, it select that intelligent pivot with the help of that MOM, median of medians. So this is about it. Yeah, I hope it's thing is the last problem, which is divide and conquer. In this also, the divide and conquer policy is doing the left off and right off. But in the left off and right off, they try to find out the median of the left off and median of the right part. So again, that parts have been finding the medians is each block they are fixed with 5. So whenever it is less than 5, directly median we are returning. If it is more than 5, we try to split it into that 5 blocks. In that 5 blocks, each block we try to find out the medians. So using that median, they sort it. That is simple. So in that way, if you go with it, the kth largest, you can easily find out it. So that's called quickest selection. So you can say that fast selection. So that is about it. I hope it's clear. Please let me know that any clarifications.
Sir, in the like previous slide, recursion tree, can you open that once?
Yes, I'll open it. It's a recursion tree. Yes.
Can you scroll down?
Yeah.
Down, sir, down.
Still okay.
Above.
Okay.
Sir, here, can you scroll down? Sir, in the
this is merge-sort. This is quicksort.
in the cupboard, sir, sort.
Merge-sort, no? Merge-sort, no?
No, the cupboard, what the name is.
This one quicksort.
So can you scroll down? In the last example, where, yeah. So here, yes.
Yeah.
So in
Here,
the Karatsuba exponential thing, like here it is n log 2 3.
Cube.
Sir, why not it is written as t thing?
See, what is it? What it doesn't written? What do you say then?
Like tn is written as tn by 3 to like plus 2. We are calling the recursion again, but in the Karatsuba
3 times only, no? Karatsuba exponential is 3 times. See, look at
but it should be written as like recursion only again. Like
recursion only. It is increasing. It is exponential growth only. Clear?
So it should be written as t to the tn equals to t bracket this one.
This one, no? This one. N to the power of that log 2 3. Is it right? You're asking log 3?
No, I'm asking why not it is written inside a recursion, like we wrote like tn by 3 or t to 2n by 3.
Okay. This recursion you're asking about, na?
Yeah, why not we wrote is a recursion?
Yes. So you are saying it is why not it is divided by 3. Quicksort is always it is doing half partition of the problem. See, the problem size is reducing Quicksort.
I got that it is.
But here you are asking why it is not doing dividing. Why this way, for example, this particular one, if it is Karatsuba is there, you are asking about T of n is nothing but, so T of n by 3, why it's not happening? You mean that like that, you know?
Why it is not like Tn log base 2 3. But it is not written in the T thing, na? I am asking that. Why
No,
it is
that expansion format was given in the Karatsuba earlier. So you can see that here. See, look at here. See, this is a complete one. See, look at 3 times. 3 times it is. So if it is expanded format when they are going like, it is simple concurrence relation. 3 times n by 2 plus n they are doing. When it is expanded, it comes to that a log value, because it is exponential growth, no?
Yeah.
So see that's earlier it was given. See, look at it was given 3 times n by 2 is done. So it is off time of the first unit, leading space, and off time of the unit place. That's 2 times is over, and then across this particular 2 numbers is happened, but after subtracting it is happening. That's the ring 3 times only. 3 times n by 2 is done. No doubt about it. But what happened, this growth is continuously going until we are getting a single digit value, which you can have, you don't have further, further splitting. So further multiplication. What do you call, last bit value. Whenever last bit value is going for that, so that what happened, it's going for the log base only, Yeah, here it is. Look at. So a log n can be rewritten like n log a. So 3 log n can be written that n log 3. So that n into 3 by 2 log n, which can be rewritten like this, like n into log 3 by 2, which is, reverse, So n will become as a base. So log 3n 3 by 2, and then it is, so log 3 minus log 2, then simply log 3 minus 1. So n1, that is 1 plus log 3 minus 1, simply 1 plus is no value for that. So what simply we can say that, so plus and minus is gone, like this one and this one is gone. So what do you call, log 3 is there. So n log 3 is there. So n log 3 is nothing but 1.5, and where it is, growth is exponential. When the growth is exponential, so definitely we are going to that power value, no? We are getting power value. So, but in the case of this one, Quicksort is there. Where is the Quicksort? Yeah, here it is Quicksort. Sorry, this is not Quicksort. Yeah, here it is simply, it is dividing. So every time it is 2 only. This is n, 2 parts, again 2 parts. It is, see, look at 2 into n is there, 2 into n is there. Simple, it is 4 into n is there. So simple multiplication. So 4 times n times. But here it is exponential growth is there. Whenever exponential growth is there, so definitely it is, so n to the power of, you have to take it. So definitely it is exponential one. So this one also exponential, this one also exponential. But these are, simply it is decreasing one. Okay. Exponential growth is happening. Whenever exponential growth is happening, so base, you can see that wherever you want to find out this one, you can find out in the complete expansion format at concurrence relation at this place. Okay. That's the reason they are not here. It is not complete expansion has been given. Only simply the final value is written. So when they have written final value, don't confuse that. You can see that complete expanded format in the earlier lecture slide. Fine. Yeah, I think we can close the session if you can say yes. So kindly look at this lectures once again. Maybe wherever that vital space is there, like, the comparison across boundaries, the comparison within that partition, because always divide and conquer is the problem subdivided one, in that sub problem how the solution is finding. After finding the sub problem solution, how they are combining is the one task. In the sub problem, how it is solution we are getting is. So these two strategies only we do the divide and conquer policies. Clear? Yeah, I think we can close the session. So thank you. Good night, all. So we can stop this call. Huh? Okay then. Yeah, thank you. Good night.
Thank you, sir.
Thank you. Bye.